Europe's latest aspirations to reach a higher energy independence from Russia is especially relevant for the heating sector of countries in temperate climate. Let's say, for example, if we have a look to Europe, it's France, Germany, Poland, and so on. And one promising key technology to reach this kind of energy independence respective to heating is the use of geothermal energy as a renewable alternative to natural gas. Well, if we have a look to the world map, I hope all of you can see it well. The green dots indicate nowadays use of geothermal power plants. While these are just the very big ones, like that also can produce electricity. So, of course, like there's a certain geological factor why the geothermal power plants are especially put into these spots, or like let's say they are built there because there's a tectonically active zones where you have a very favorable geothermal gradient, what means you can reach high temperatures in a relatively close depth in the underground. But if we have a look to Europe, for example, there's also the question, apart from the geothermal gradient that I just mentioned, there's the big question, why does not every country heat their buildings with geothermal energy? And so just like as a very simple question, and the answer is like due to the risk and like the exploration risks that occur due to uncertainties in the subsurface. Well, if you compare to other sources of energy, if you have solar power and wind energy, you can calculate quite well the annual average of your location and like how much sun you get or how much wind you get in average, and you can calculate kind of the output of your investment. While the risk for exploration is super high in the underground, since you have to drill a borehole first, or like you do first a geophysical, let's say geophysical, like if you have the underground here, you do just a geophysical assessment, like non-destructive, then you interpret the underground and make a guess how feasible your project is. But at the end, you will finally just know if the project works if you drill a deep borehole somewhere in the reservoir down there, and make a well test, and then you see if all the investment of drilling your borehole was worth it or not. And this is a super high risk, and that's what we are kind of working on to minimize the risk, kind of. And there's a lot of uncertainty in measurement data because we usually just have a single well, just because of the costs again, because if you have this one well, of course it would be favorable if we would have a lot of wells. Like if this is now just a cross section or a top view of our subsurface, and this would be our reservoir, like we look from the top on our reservoir, it would be super cool for a very good assessment of our reservoir if we would have a lot of wells, like in the left picture, or in the left part of our screen, like this one. But the reality is usually that we have a very small amount of wells, like this. If we have 2, that's already kind of a lot. Depends on because the costs increase with depth. Like if you go 4,000 or 5,000 meters deep, it's super expensive to drill already 2 wells. Like can be several million euros investment already. So this is kind of the regime that we are working in, and that are the data that we kind of get, like now from the spatial perspective. Well, now I gave you kind of the introduction to which data do we have, what are the risks, and now I would have a look, like just tell shortly about existing methods that we have, because we do have already methods which we try to investigate our subsurface. Like mainly what we know or what we use is in like the geomodeling, like the numerical models. But what is the problem in numerical models, or like what is a limitation that they're facing, is on the one hand noisy data, because the data are not ideal that you get from such a well. Like I don't know if I mentioned, like these are the injection wells. like where you do well testing and measure your pressure. But the data might be noisy due to several reasons, and these are like limiting factors for numeric models. Another big limiting factor are fractures, like fractures in this way, because fractures cause a scaling problem. Scaling problem in this way means that, for example, if this space is several kilometers and we do have a fracture in there, which has an opening, let's say, fracture aperture or opening width of a few nanometers, that causes in numerical modeling, like if you are talking about finite element methods, it causes a big problem in the meshing. Like, I don't know if all of you are familiar with, but like if you have to kind of model certain finite elements, and they have to be, the mesh around this part of around this fracture has to be much finer, like with a much finer element width than around here. So this is called scaling problem, what causes you maybe to have several hundred thousands of elements in your mesh, and what then in consequence causes like high computational costs. So this was just about the limitations of existing methods. What leads us to the main topic of today, or the so-called physics-informed neural networks. Well, in this particular, I called it flow PINN, what means flow, like for hydraulic flow, and physics-informed neural networks, PINN is the abbreviation for it. And especially today's topic, like application of these physics-informed neural networks in subsurface flow. And just to give a short overview, like where to put these physics-informed neural networks, because maybe you heard all of this word, like these terms like machine learning and physics-informed neural networks. You heard of them before, but it's maybe good to locate these terms kind of. So machine learning in general, I would just give it a short overview. Machine learning is like to give the very biggest general formulation, is like where a computer algorithm learns to find a certain pattern and features in a big data regime. And we do have on the one hand, and on the one side, we do have unsupervised machine learning, this is kind of what is special about unsupervised learning, that we don't know what the output should be of our algorithm. So this is used in very, very large data regimes. Like the most famous ones are, like, let's say the Google search or the Instagram feed. So Google doesn't know which should be the output of the algorithm. They just have one, let's say one objective, and that is sell, like that you should watch the advertisements as long as possible, that you buy your product. But what the algorithm does is kind of a black box. Well, that's not our topic. I just mentioned it, that we use supervised machine learning, and in particular, like regression. So I mean, probably all of you heard already about regression as a general thing, like that we are fitting a certain data, like a function in a certain certain data set. And how does regression work with neural networks? I would like to explain briefly. So let's say we have a certain data set. These dots, green dots and blue dots, are our data set. And why do we distinguish between them is that the blue data set is used to train a neural network. So we do have here like certain values of x, and we give these values to our neural network, and the neural network should make a certain suggestion for each x value, suggest the respective y value. And we use only the blue dots for testing, for training, and after maybe the first suggestion of the neural network is just this. So just in the first iteration, a very bad suggestion, and then the error is calculated for each and our function. And like after we calculate this error or loss, that's like also the right term is loss, then there's a certain algorithm called backpropagation that calculates how the neural network, or how parameters inside the neural network should be adjusted to make a new suggestion. And after this is a loop, kind of a process of iteration, and after a lot of iterations, maybe we get such a curve. And then we evaluate this curve also on the testing data. The testing data are the data that the neural network didn't know. Like we just use it after the training. We test the neural network, the accuracy of the neural network, and see if it generalizes well. Like you call it generalization, and if it generalizes well, it hits also the green dots very well. So this is just the general functionality of the neural network, and I should use maybe red color, because red color is the regression. Okay, and now I will show you some example regression that I performed for some real, or like for some physical data. It works like this, that I run a model in OpenGeosys. OpenGeosys is just a finite element code for example, like modeling subsurface flow. And we just have a very simple 1D regime from 1 to 10 meters. I put the boundary condition of let's say 1 megapascal on the left side, like on 0 meters, and on 10 meters, we put the boundary condition of 0 megapascal, or respectively 1 and 2, like the difference is still 1 megapascal. And then we produce like the evolution of the pressure over time. So over several hours, like from 19 hours, we have here the first example, to 85 hours. Like this is by time, the evolution of the pressure. And this graph looks kind of similar in this way, like the previous one, that we have training data points, in this case blue, and validation data points, which are yellow. And what is kind of very clear to see, like for such many data points, like for such many training data points, our model does a good job in regression, because it should be super easy for it, like to match all these, to match our red line through all these points. And what you can also see here on the right is the loss history, and it shows two losses, like the blue or the green loss is the loss for the training, like that, which reduces over our iteration or epochs. Like these are these loops that I explained before. Like, after quite fast, after a certain loops, it's already in this kind of constant loss range. And what is particular here, that not only the loss for our training data points, for the blue training data points, is low, but the validation loss has the same kind of height. What means that our model generalizes well. And as we can see then on the next slide, so what is the general intention here is I reduce data points, because the reality is we don't have 712 data points, or we don't have so many data points, especially over space in a reservoir. So this is a simple example over 10 meters, but the general idea is we don't have so many data points over space in a reservoir, because each data point is like, for each space is an observation well, and this would be a lot of observation wells. And so here we reduce the amount of data points. Now I just picked one single time step, like 11 hours as an example, and I pick 25 training data points, like by random sampling on this line, and again make this trained neural network, and then make a prediction for our validation data points for the yellow one. And the difference between the previous graph and this graph is that the generalization is not as good as before. And this is probably because we have less training data points. Generalization means for all points on the blue curve where it's not a training data point, like the red curve doesn't do such a good job in prediction. I don't know if it's clearly understandable. Maybe you can also ask a question if it's not later. But here we see like our red curve leaves the blue curve. And this means our model doesn't generalize super well. And this can be also seen in the right graph, like that our loss for the green loss is lower than our validation loss. So this is just what the right graph shows, what I explained you in the left one, so that it doesn't generalize so well. And if you go for a more extreme case and reduce our training data points even more, and just have 6 data points on our curve, then the generalization performance gets worse, or like the neural network has a worse training result, and it, for example, here it doesn't match the curve at all. So it just in comparison to the previous one, it looks not as good. So why am I telling you this? Because we are now leading to the physics-informed neural network that I just announced before, and physics-informed neural networks are necessary for this case because we in the reality of our subsurface problem, we just have a very few observation wells, or like wells where we can perform a well test. So the idea is that for all the intermediate space between, let's say, one observation well and another one, we could just calculate the physics in between and have kind of more information about the course of our curve. So you saw this picture again before, and I'm just putting it again just to remind you what I told before, like that we have just a few observation wells in the reality. And this is a graph that shows where physics-informed neural networks or physics-informed machine learning makes sense. It's exactly where we have just some data and not lots of data, because all the classic machine learning uses a lot of data. This is like their main. This is kind of the main advantage to perform or to process a lot of data. And since we don't have so many data, we have the idea like to apply physics-informed neural networks or machine learning. And now is the question: how does a physics-informed neural network work on the contrary to a normal neural network? A normal neural network looks like this box that you can just see here, and it works like this. Now we have two variables. We have space and time, and in the regression that I showed you in the beginning, we just had space. But the neural network is, let's say, quite a simple fitting algorithm, and you just give it a time and a space value, and then it makes a suggestion for our U. In this case here, it's hydraulic head. And the thing is, if we would have now our domain, let's again think of our reservoir with the top view, we would only have the information of our real U, like that we could measure, or we would have it only on our well in the center and on the boundaries, like let's say like this. But for the space in between, we don't know anything about our U. And that's why we calculate the physics, like diffusion or like our mass balance equation. And with this, we try to get an information like how our pressure can be like in between, like our well in the center and our boundary. And with this kind of calculation, we can now assess in the loss if the suggestion of the neural network for the pressure over time and space is good or not. And usually it starts really bad, and then you tell the neural network, like after calculating or like after comparing, you tell the neural network, okay, make another suggestion. And over hundreds of suggestions, the neural network makes a better fit of our pressure or like hydraulic head over space. So that's kind of the principle. What I just told you before, this is now what I'm using right now as a calculation. This is, again, as you remember before, this is our 1D domain, now scaled from 1 meter, 0 to 1 meter. And second dimension, now take care, that's not space, like that's not the second space dimension, that's time. And here for this domain, or like for this problem, we know our measurement data or like our observation data are the green ones, like for initial condition at time 0. This is where we know, so we say there the pressure is just homogeneously like even over the whole domain. And then we know over the time, we set the boundary condition that remains like constant or has a certain value, and our other boundary conditions. So 2 boundary conditions and 1 initial condition. And we have the purple dots, and the purple dots are not observation wells. These are points where we calculate, or where we make like the calculation with the PDE, like with our partial differential equation with the mass balance equation. exactly, and to calculate here the loss for the difference between our PDE result and the suggestion of the neural network. So actually, I want to include, I was thinking if I should include this slide, but I just decided that I will. So I'm right now performing this physics-informed neural network. And right now it just remains a challenge. Just to remind, like I'm in the first year of my PhD. So I'm beginning, or like I'm now using the PINN, and we have a certain problem here. That's why things don't work right now as they should. But like how the idea would be now that our like our truth values, you remember maybe like this pressure diffusion over a certain space, our prediction, like our dashed values, should be perfectly on each line of the pressure, and they are not right now. Yeah. So this is connected to some details of physics-informed neural network. For example, that you have to make a dimensionless formulation of your PDEs, and maybe there's a certain bug right now. And yeah, so that's where I am right now, and yeah, that's my challenge. And also the thing is that the output of neural networks and also physics-informed neural networks is not always the same. Like you can train it 2 times or like and get slightly different results. So this is called like maybe robustness, and this is also another challenge that we are working on right now. And I was just mentioning certain future features because I was telling you right now only about the flow because this is the most simple, like the most simple prototype that one can do, like with just one PDE and in 1D. So that's I'm doing right now the simplest case to get a working physics-informed neural network. But the idea is to raise complexity, to make like a 3D reservoir model, to maybe use multiple processes, and then to also incorporate inhomogeneous materials, because that's the main challenge, as I just told you in the beginning. Like if we have our domain and we have different, let's say, diffusion or like permeability over the domain, or we might have certain fractures somewhere, like if red is our well in the center. Yeah. So this is right now, this will be next steps of my work. And then one idea was if we maybe set very specific injection regimes, if this could, make it easier for the neural network to guess the pressure, or if we make like an inverse problem to guess the material parameters of the domain, if this could help to guess the permeability, for example, of our domain if we use an cyclic injection. Yeah, if we talk about limitations of PINN, because right now I was just telling that PINN have a lot of, let's say, just opportunities. Well, the challenges are that in forward modeling, like in traditional forward modeling, what means you know your material parameters and you model like your pressure, for example. The numerical models are still faster. Like PINN are better in handling the noisy data, but apart from that, like right now, the normal FEM has a faster computation. And on the other hand, the limitation is that they are it's a very indirect method. If we go back to the slide, to this slide, like, oh, what's happening? Okay, now everything's here. And if you go back to this slide, we just use the physics outside of our neural network. I hope it's understandable. Like it's an indirect method because we use the physics to calculate the loss. But there are more advanced approaches where you use the physics directly inside your neural network. Well, that's more more efficient in calculation, but more difficult to implement. So this is like a more advanced version. which might be another step after I finished with the PINN kind of. Yeah. So, but this is what I would mention as also as a limitation of PINN. And yeah, maybe as a take-home message, that PINN have a very large potential in subsurface modeling because they can handle noise data in a scarce data regime. So this is maybe what you, and all the rest, like future results of modeling, I would then be happy to present in the follow-up presentation of this one. These are my references, and if there are further questions for details about like the neural networks, I have some info in the appendix if you're interested. So are there any questions regarding this topic?
Okay, thank you, Linus. Well, I don't know, questions? I have a question a little bit about, you put a mesh balance, for instance, I noted it, I wrote it down, slide 15.
This one, right?
Yeah. It seems to me that of course, you can sort of estimate or predict this U and also the derivatives of that, but then you put there something which is like a mesh balance, but this is sort of you impose it, or you just use it to evaluate the error or something.
We're using it only to evaluate the error, exactly.
Yeah.
So, but here in this formulation, like if we have our, like this is, I think, diffusion coefficient. So this is dependent on material parameters. So here we have to still give we have to define material parameters in advance. You know what I mean? Like like permeability and dynamic viscosity and so on.
Yeah. But of course, there are various parameters which you can evaluate, etc. Which you can have.
What means we have a similar problem in these ways, like the numerical modeling, because they have the same. You know what I mean? They have also the same problem of guessing material parameters, and maybe in the future we can use another neural network. But that's, I think some scientists investigated on that, like to have a second neural network that proposes also the permeability. So in these ways, there's a high flexibility, but yeah, a lot of try and error maybe also.
Yeah, but okay. But so then another question, because you use this mesh balance or you calculate the mesh balance error, but you don't compare with direct calculations or something.
What do you mean with direct calculation?
Well, with direct modeling, let's say the classical numerical modeling, you cannot do a comparison with that, or?
I'm not sure. You mean if?
Or you can make a normal numerical model that simulates the physics.
Yeah. If we
Given parameters, and I thought that was what you used to calculate the error during a learning process. For instance, here you have the blue line, which is the ground truth.
The ground truth is calculated by it's a virtual data set. Like it's not the data set that we have from measurements, but it's calculated by a numeric code, like our ground truth. And now but it's just a virtual experiment, because in reality I wouldn't do it like this. You know what I mean? Like in reality I wouldn't have this ground truth from
I thought
OGS.
that it was a sort of actually what you would have are your training data points, no?
Sorry again. The training data points I obtained from our ground truth.
Yeah. But I was imagining that the blue points, the training data points, you got from it's a model, a numerical model, a direct numerical model, or not?
Yeah.
How do you get to? How do you get your training data
The
points?
training data points are like, I mean, this, as I said, it's like now it's a virtual experiment. So the training data set, or like the whole data set, is an output of my numerical model. But in reality, these training data points would be observation data, like would be data points from a well test.
Okay.
Maybe I was a bit confusing.
Yeah, of course. Yeah. Then I understand. Yeah. Okay. So this is just the idea is to.
And now in the extreme example, maybe here it becomes clear. In the extreme example, we have only, like this is the extreme example. Here we don't have any, like in the red, like, or in the purple domain, we don't have any training data points. We just calculate the physics. You know what I mean? Like we only have training data points for the boundary, because there we decide. There we can assume a certain pressure, but inside the domain we don't know.
Yeah. Okay. I got it now. Okay. Thank you.
Yeah, thank you for the question.
Other questions or comments or whatever? If not, then I thank Linus for his presentation, and the rest for attending. And then I think we can close this seminar.
So thank you very much.
Okay. So maybe I see you next week. Okay. Bye bye.
Bye bye.